now I must offer up two confessions to the spirit of Charles Augustin Coulomb. I've actually been doing two things with his law that are a little not so good, okay? So what I've been doing all this time is drawing something like this, putting a plus Q on it, and saying we're going to use Coulomb's law to get the electric field. Two things, a little questionable about that. One is that you don't use Coulomb's law to get the electric field, right? We know what is Coulomb's law? It is the force between two charges. It's not the electric field between two charges, it's the force. However, since we basically define the electric field in terms of the force, since it's basically this force F and you just divide it by the Q, to me it's kind of the same thing. So I like to say we're using Coulomb's law to get the electric field. That one, I believe, is forgivable, although maybe I'll get a lot of hate mail about that as we go in the semester. I don't know because it's only July. The other one is that I draw this. I often draw this sort of round thing and put a Q on it, and we calculate or we apply Coulomb's law. When Coulomb's law actually only applies to point particles, it doesn't apply to a big chunk of charge. I've been implying chunks of charge. I think I even said chunk of charge a few times. Coulomb's law really means a point particle, and the point particle we usually think of as at the origin, and we move different radii away from the particle. Here, this has a big radius to it already, and we move even further away. So is that okay? So that's what we're going to find out now when we do Gauss's law for a sphere of charge. Okay? What I've been drawing is basically little spheres, solid spheres of charge. I'm going to draw it a little bit bigger so that, it'll look better when we do Gauss's law. So here, now, let's say we have a sphere. It comes around and goes back like that, and its origin is there, and it has a radius A, okay? And it has a total charge plus Q. When you work on these things, you have to decide, when you're doing solid charges with rho, when you're doing a solid charge density, you have to decide if you're going to think about it as a volume and a total charge Q, or if you're going to think of the charge density. They're really basically the same. So you can either say this thing is Q, and its volume is what? Its volume is the volume of a sphere, 4/3 pi, in this case the radius is A, cubed. Or you can work in terms of the charge density. So here in the problem, I'm telling you that the charge Q is uniformly distributed throughout this entire volume. Therefore, you can define rho. That's a bad rho. Rho is what? Well, it's just Q over 4/3 pi A cubed. So you'll see later how you can do it either way. You can think about either one when you do Gauss's law, whichever one makes you happier. Okay? So now the problem is set up. Solid sphere of charge Q, radius A. We have all these parameters here. The first thing in a Gauss's law problem is symmetry. What is the symmetry telling us about this problem? Well, if you pick a point anywhere, say here, the electric field can only be along one axis. It has to be along the axis between the center of the sphere and the point. The E field can only be this way or this way, okay? And it's a standard symmetry argument. If there were some charge over here creating a field with this component, there would be some charge down here creating a field with that component. All those components would cancel, and there would be no field in the lateral direction. It has to be this way or that way. The other symmetry argument is it can't be this way or this way because neither one is special, right? There's nothing special about that way. It looks the same no matter how you go around this axis. Therefore, the E field has to be 0. So basically, in this case, symmetry says that E is always radial, or is always points in the radial direction away from the center. Okay? So that's all we need to know. So now we're going to use Gauss's law to figure out what is the electric field. In this case, we have two special regions. Since we have a volume charge density, we can be inside the charge or we can be outside the charge. And we want to sort of solve those separately because they're different places and the Gauss's law application will come out different. So let's do this. Let's do, let's separate that off there. And let's do R is less than A. So that's the region of space where the radius starts here, the origin is 0, and it gets bigger and bigger. As long as radius is smaller than a, it's up to here. So that's basically inside the sphere. So inside. All right, so let's apply Gauss's law. Integral of E dot dA equals Q enclosed over epsilon naught. All right, let's see. Well, what we would want to do is I'm going to clean up my diagram a little bit here to make it clear. And we want to pick our Gaussian surface, and we've already decided that we have spherical symmetry. So as you can imagine, we want to pick a spherical Gaussian surface. Okay, so I'm going to draw just another sphere inside the big sphere, like that. And it's also our Gaussian surface. Okay, so let's apply E dot dA to that. So due to symmetry, as you go around the integral, everywhere you go, E has to be in the radial direction, and dA, the A has to be in the radial direction. It always points out. E and dA are always in the same direction. So the dot product goes away. Okay. E has to be constant, because as you go around this Gaussian sphere inside the big sphere, there's nothing special. You're always at the same distance from the origin anywhere you go, so E is not going to change. So it's a standard symmetry simplification, is you just have a constant E. The integral of dA is just the surface area of a sphere. Right? So the surface area of the sphere is 4 pi, and it's r squared, because the sphere of charge has a radius a. We're doing a Gaussian surface out to some radius r. So 4 pi r squared. Okay. That's the left side. The right side is the enclosed charge. That's a little trickier here. So we want just the charge inside this sphere, not the part that's on the outside of the Gaussian surface in the entire thing. So, well, the simple way is just to literally say it's rho times the volume. So we could just say it's rho, which is Q over 4/3 pi a cubed times the volume, which is 4/3 pi r cubed. Okay. Looks kind of messy, but that's a standard thing to do. Right? The rho is the charge divided by the whole volume times the volume of just the Gaussian surface. And the good news is a lot of that cancels. The 4/3 go away, the pi goes away, a lot of it goes away. Okay. And let's see what is left then if we bring this 4 pi under here. In the end, what do we have? We have E is, let's see, so that r cubed and that r squared are going to cancel, and we're going to have Q over 4 pi epsilon naught, and we're going to be left with an r up here and an a cubed down there. So we get that the electric field as you move away is actually increasing. It's linearly increasing in r. Okay? It's 0 at the origin, which it should be. By symmetry, you could argue that the field has to be 0 at the origin. And it just goes up as a linear function until you get to a, where this equation is no longer valid. Right? It only applies up to a, because when you go outside of a, if your Gaussian surface gets bigger, then the amount of charge inside is now different. So let's do the outside now. So the outside is r greater than a. All right. All right, so the integral around the closed surface of E dot dA is Q enclosed over epsilon naught. If you're just waking up, that's Gauss's law. So hopefully you've now got that down as Gauss's law. And now we're doing a sphere out here. Right. Sphere, you know, it's centered on the origin. It has a constant radius r, but it's outside. Well, all the arguments are the same. The E field has to be along the radial direction. A has to be along the radial direction because it's a sphere. They're the same direction. The dot product goes away. The E field has to be constant because it's all in the same radius around the sphere. So again, you just get E. And the area of the Gaussian surface, it's at radius r. It's 4 pi r squared. E equals Q enclosed. Well, that's much easier this time because it encloses the entire charge. So it's just plus Q over epsilon naught. So if we solve that for E, we get something that looks familiar. 1 over 4 pi epsilon naught q over r squared. So this is inside and this is outside, and they're all in the r hat direction, or they're all in a radial direction. And you will see that the spirit of Coulomb will forgive me, because as long as you're outside the charge, it does obey Coulomb's law. Right? This is Coulomb's constant, 1 over 4 pi epsilon naught. It's basically Ke q over r squared. So what that's saying is, as long as you're outside this spherical thing, it acts like all the charge is at a point at the center. So you can always treat a spherical distribution of charge as though it's really a point charge, as long as you're on the outside. It actually does have to be spherical. So in all my little plus q's, hopefully it looked fairly spherical. If it becomes not spherical, then it behaves a little bit differently. Okay, so that's the sphere.